Thank you very much, Sarah, and thank you very much for having me here. It's an honor to speak here. I'd like to talk about some joint work with Tony Carbery and Wang, and our object of interest is the extension operator in harmonic analysis. So an extension operator is just a Fourier transform, but of very specific functions, of functions defined on curved surfaces. And we want to understand the properties of these extension operators. So the problem I'm going to talk about today is open even in 2 dimensions. So for simplicity, I'll write everything in R2. Okay. So instead of taking a compact patch of the surface, we just take a curve, compact patch of the curve. So think of it as a strictly convex curve in R2. It could be a circle or the parabola. And let's take any function defined on that curve and understand its Fourier transform. That's the goal. For us, it is there is no problem to assume that the patch we're considering has normals that are close to being vertical. So they're about a 1/100-degree angle from the vertical direction. The normals. And instead of thinking of the function as defined on this curve, we can think of it as defined on the line right below. So here is the domain of our function, and we can pretend it's actually defined right above. And S of y is the parameterization of our curve f. Okay, so what is the Fourier transform or extension operator of such a function g? Well, it's defined on the whole of R2, so 1 dimension higher than the curve. And for every x, we are doing as usual, we're taking the integral of g, but against a twist. So the twist has a phase function right here, which is the inner product of this x with the general point S of y of the curve we are integrating on, where g is defined. So this is an object of interest for many fields. For instance, if according to what the curve on the left is, or surface, this extension operator can be the solution to some PDE. For instance, if we start with a paraboloid on the left, the extension operator would be the general solution to the linear Schrödinger equation. If we start with a cone, we get the solution to the wave equation. If we start with a sphere, we get the Helmholtz equation, and so on. So this is of interest to PDE, for instance. But for other reasons as well, we care about it. For example, in number theory, Fourier analysis can be used to count solutions to the Diophantine equations. And understanding this object, the extension operator, people managed to prove the main conjecture in the of mean value theorem in 2015. Okay, so we want to understand things about this object, and we understand some things. In particular, if we focus our attention on a big ball of radius r, then we understand what the extension operator looks like of functions defined on tiny, tiny arcs on the left. So the arcs have to be very small. In particular, their length has to be this big arc, the -1/2. And mainly, you can think of it as a rectangle of length r to the -1/2 and very small height, r to the -1. So by the uncertainty principle, if you get any function defined on this rectangle, its Fourier transform or extension operator is essentially constant in magnitude in dual rectangles or tubes. So they have r to the half width and r length. Specifically, if you get the indicator function of this cap, or just a smooth version of it, and you take the extension operator of that indicator function, it will actually, painstakingly, be supported in such a cube through 0. And the cube points to the normal to the cap. That's very important. Now, if you take a general function instead, you can write it as a Fourier series. So a Fourier series is a sum of modulations of the indicator function. So each summand of the Fourier series will have Fourier transform supported in one of the parallel cubes in that direction. Okay. So this gives rise to the wave packet decomposition, as we call it, of the function on this cap. So sorry for the background, but we needed to understand what's coming. So here it's the wave packet decomposition of G restricted on this cap, theta here. We write it as a Fourier series, as we said. This GT are the summands, and they are parameterized by the cube C pointing to the normal to the cap. And each GT is the summand whose extension operator is supported in the corresponding cube T. Okay. Any two summands in the Fourier series are orthogonal to each other. And not only is the extension operator of GT supported in T, it's roughly constant in magnitude there. So all this stuff is heuristics, but there are ways to make them more precise. Okay? For now, we can imagine that these things are correct. Okay. Now if you take another cup, it has another normal because of the curvature we assumed. It's not a flat curve, it's a curved curve. So it gives rise to another family of cubes. And the extension operator of any function here in this blue cup will evolve like a sum of waves, each wave being in a different one of these blue cubes here, pointing to the new norm. So from each single cup, the waves don't interact with each other, the waves corresponding to that cup. Okay, and putting together all the wave packet decompositions coming from the different cups, we get the wave packet decomposition of the whole function G here. So we write it as summons like this, and any two summons are orthogonal to each other. We explained it if they come from the same cup. And if they come from different cups, then they have disjoint support, so they're orthogonal. So this first property implies that the Pythagorean theorem holds for this function G. We can understand its two norms in terms of the two norms of the wave packets. The second property, as we said, is that the extension operator of every GP is supported and essentially constant in magnitude on the corresponding tube T. Okay. So from this second property, we see that if we want to understand the operator at some point X, we only need to consider the tubes that pass through X and add up their contributions. We don't care about what happens to the tubes that don't pass through X. And you see that because we're seeing some curvature on our curve, it's not a flat curve, the tubes through X pass through, have different directions. And for that reason, we expect that the waves that they carry will be out of sync a lot, and they will cancel each other out a lot. And that is the restriction conjecture. It says that this cancellation of the waves whenever they meet is so intense that for a very large range of exponents P, the P norm of the extension operator is controlled by the P norm of the initial data G, even though the extension operator is defined in one dimension higher than the function G. We only know this is true in two dimensions. But as I said, the problem I will talk about today is open in two dimensions also. Let's just understand what the conjecture says a bit, because it's useful. So it holds for P equal to infinity, so for very large P. Why? That's very easy. We just need to control the magnitude of every value of the operator. So the absolute value, can put it inside the integral, and it's at most the one norm. And because we're in a compact set, it's at most the infinity norm of the compact. Okay, but as you lower your P, maybe it stops being true, this conjecture. And in fact, for P equal to 2, it fails dramatically because the left-hand side is infinite. So we'll explain that because we will need it in a moment. But for now, think that if this extension operator was actually the solution to the Schrödinger equation, the space-time solution, then at every time you have preservation of energy for the solution, which means that the two norms stays the same throughout time. So if you integrate over all time, you get an infinite norm. Okay, so this is the picture. At infinity, the conjecture holds. At some point from infinity all the way down to 2, it should start failing. And the conjecture suggests the exact point where this switch of behavior happens. We have proved, people have proved that it's the point suggested holds in two dimensions. That's the point 4. P equals 4 in two dimensions, but in other higher dimensions, it's still open. Okay. But even if we knew fully the restriction conjecture holds, it would tell us that it is an estimate on the level sets of the operator, on the size of the level sets. It would tell us that the level sets of the operator can't be very big. So the operator can't be big at too many points. But it wouldn't tell us anything about how the level sets are distributed in space. It would give no structural information on the extension operator. And the conjecture I'll talk about today is about understanding some of the structure of the level sets. Okay. And it's actually, the conjecture we'll talk about today is L2 based, and 2 is not the point where restriction works. Okay, so this is the conjecture. you throw an arbitrary weight in your picture. So you can think of it as a characteristic function. Let's think in this talk it's a characteristic function, and it's a union of balls of radius 1, so tiny little spots all around. And we want to understand how the operator behaves on this arbitrary blue space in terms of its two norms. So we want to control the operator squared on the blue part by the two norm of the initial data. And there should be some loss here at the front. Question is, what is that loss? And it should be a loss that has to do with the structure of the blue set, if we're talking about structure. And the conjecture suggests that the correct loss here, a correct loss, would be the largest line integral of the wave. So you take all the lines in the picture, you look at the integral of the weight along all these lines, and you pick the largest one. That's the infinity norm of the X-ray transform. So the X-ray transform of the weight would take any line and would return the integral along that line. We want to take the largest value of this. Okay, so just to pictorially understand the conjecture a bit, we'll just try to see what happens with the two norms of the operator at any given time. First of all, as to say, we only know the conjecture holds in very special cases. One case is when the weight, the blue set, is radial. And the other case is when the blue set, the weight, is contained in the one neighborhood of the circle. So these are extremely special cases, and they follow from Bessel functions. But in any other case, the conjecture is open.
When you say it follows from Bessel function, just estimates for the decay of Bessel functions or something more subtle?
Well, it is actually a very elegant argument. It's not very hard. It is elegant, but not too subtle in terms of.
Yeah, I'm just asking. You know, Bessel functions are complicated if you have the order. And
yeah, it's just about their decay.
Just about
their decay.
Okay.
Yeah. Okay. So we want to say something about other weights, other than these. And let's just try to understand the conjecture visually. So a basic property, as we said, of the operator, the extension operator, is that if you take the two norm along any horizontal line, you're going to get back the same number. So let's just try to understand that. Let's take the arbitrary point x comma t naught of this line and try to calculate the operator there. So in the phase function, we have the inner product of x comma t naught with the arbitrary point y, sigma y of the curve where we pretend our g is defined. And this sum was split in a product of two exponentials like this. So here we have a function of y that is simply a modulation of the original g. And y is a variable in R, okay, just like x. So this is a standard Fourier transform of whatever this modulation is. So when you try to look at the two norm on this line, it's the same as the two norm of this Fourier transform. By Lanzarel's theorem, you can lose the hat. So you're looking at the two norm of this modulation, and the modulation of G has the same modulus everywhere as G itself. So you always get the same two norm as the initial data, no matter what line, horizontal line you integrate at. So that's for every horizontal line, you have an explicit formula for the two norm. And the same would hold if you slightly tilted your line. So you would do a parameterization of these new lines instead, follow the same argument as before, and some Jacobian would come out. If you make sure that these lines are not too tilted, so their directions sort of stay clear of the normals to your function, then the Jacobian is coming. Okay, so this is nice. And here is maybe a way to feel what the conjecture says. I've rewritten it here. So here on the left, we have the function g. On the right, we have an arbitrary weight, indicator function. And it's accepted that in this largest line integral, I shouldn't really be looking at all the lines in the picture here. I should be looking at those lines that point in the wave towards the direction where the waves propagate. So the waves, remember, are revolving inside tubes, pointing to the normals here. So these are the directions of the lines I should be caring about. So amongst these directions, which line is there a line, which line in this picture contains most of the weight? It should be this one here. Right? This seems like it contains most of the balls. So this red quantity is the number of balls along this line. Okay. Now, how about the other quantity on the right-hand side? Is the 2 norm of J squared. Of course, it appears on the left because Z is defined on the left, but does it appear on the right as well? Well, this line here is sort of merely vertical. So any orthogonal line to that is merely horizontal. And we know that the operator has a fixed norm along all those lines perpendicular to the red one. So I'm counting this norm as many times as the blue balls are along this red line. For every one of them, I draw a green line through and then integrating the operator squared there. So the right-hand side, it's just the integral of the operator squared on the green part. So, and this conjecture says that the operator squared has smaller integral on the blue part than on the green part. And that's how we start feeling that this should have some structural information about the level sets, because the blue part on the left has these balls that were not accounted for on the right. And theoretically, the operator could be huge there. We are missing those values on the right. So even so, the green part should give a big integral. So, another way to see the structural information is to think of the weight as just being the indicator function of one of the level sets of the operator. So take a level set of the operator, just look at the operator there on the level set. If you rearrange here, the conjecture will say that the level set has to cluster along some line in some sense. One of the lines will have to contain a lot of the level set relative to the other quantities in the problem. What we want to do is look at the big ball of radius r and focus only on that ball on the left-hand side and do a wave packet decomposition at that scale. So split the domain of J in small arcs of length r to the -1/2, like we said before. Look at the wave packets and their extension operators coming from this picture and see how they interact, and hopefully get some. Everything we'll do will be accompanied by losses of the form of r to the epsilon times a constant for every epsilon, but that is not important. We don't really get anything near as good as this anyway, so that's fine. Okay. So what can we do with wave packets? So we can prove the conjecture holds for some very convenient weights that are not so interesting in that sense. So convenient, I mean that they're just good enough so that with some very basic properties of the operator, like some induction on scale, some local constancy of the operator, the problem becomes combinatorial entirely, and you can just count everything and it works. These are just weights that are good enough for this to work. So they don't tell you much about the operator itself. In any case, we can reprove the radial case using this wave packet analysis. And there are also some generalizations. So how do you create a radial weight? You take a circle and you keep dilating it. We could just take another simple closed curve, whose curvature is bounded away from 0, and keep dilating that one. And we can prove it for such weights as well. And also for other patches of curves, like one neighborhoods of curves, such that their tangents are nearly horizontal, so they are give or take 45 degrees from the horizontal values. So the slopes are sort of controlled, but the important thing here is that these patches should be quite long. So the tubes we have carrying the wave packets, if you take any tube intersecting this, they should cross it from one side to the other. This should be R2 long. Maybe you can see, for instance, here that like this bit of the radial weight of this weight here looks like a union of patches of that sort. So this is used for that, for instance. Anyway, as I said, it's not very important. What we really want is use theorems that have to do with the structure of the operator, of the extension operator in its level sets. And any such theorem could give us something interesting. So the coupling estimates do that. and we'll see how. But using those, we can prove something that's non-trivial at least, that the conjecture holds with laws R2/3. In a big ball of radius R, we get the right-hand side you wanted times R2/3. And that is not trivial, yes.
The best exponent known?
Sorry?
Is 1/3 the best that's known today?
Yeah. So actually, if you use, so Larry Good gave a talk in March explaining that if you use decoupling alone, you cannot do any better than R2/3. So this is the best possible with decoupling. So then after we discuss this, we'll see a bit of the combinatorial arguments from the previous weights and get some motivation to see if we can do better than R2/3 in some cases. Okay, so for now, let's just see why wave packets could be useful and why the problem is difficult. Okay. So for every single wave packet, so if the extension operator is just a single wave evolving inside the single cube, constant in magnitude there, for every such wave packet, the conjecture holds. So why is this true? We said that if we have a single wave packet, the operator is roughly constant in magnitude there, right? So whatever happens on the blue bar, where the weight is, it's a tiny proportion of what happens in the whole picture. And we want to use that to control the mass of the operator. So specifically, if you look at any single one of these balls, the operator there is just its fair proportion of what it is on the whole, if it's integral on the whole line segment. Okay. So it's just, you take the integral on the whole line and you divide with the width R2/2. And this line segment is roughly horizontal. So as we explained earlier by Plancherel, this is at most the 2 norm of the initial data squared. Okay, so we have a uniform upper bound for every single one of these balls, and you just add up overall balls to look at the mass of the operator in the blue set. This factor here is the loss from L2 to L2, and it is indeed at most the largest line integral, because here we look at all the balls in this cube, and we're dividing by the width. So this is at most the maximal number of balls contained in any of these lines in that direction. Okay. So that's fine. And the same would hold by the same argument if you had a bunch of parallel cubes, for instance. So in other words, the conjecture holds for any function defined on such a tiny cap, not just the single wave packet, but many wave packets that contain the wave. These waves, so for any function like this, you write it as a sum of wave packets, they're all parallel to each other and they don't interact with each other. And because the conjecture holds for each one, you get it for the whole picture. So for tiny arcs, we're okay. Question is, how do you start enlarging the size of the arcs to eventually cover the whole patch of the surface? Okay. And the question comes to mind that is a natural generalization of what we just talked about. If we take any function and write it as a sum of wave packets, could we decouple the contribution of this function into the contributions of the individual wave packets? Could that be true in general, not just in the last example? So if yes, we would be done, the conjecture would be solved, because you just know that for each wave packet, the conjecture holds, you get this loss at the front. So you just add up overall wave packets. And on the right-hand side, you have orthogonality, like the Pythagorean theorem holding for G. This is just the integral of G squared. See the right-hand side of the conjecture appearing there. Okay, so that would be great. And it would mean something very specific that maybe would be like someone's first inclination to try. You have a square here. You have a function that is a sum of things. You could expand out the square. You could write it as this sum times itself. So you get a bunch of sums of products, overall T and T prime, overall cubes T and T prime, get the corresponding product of the extension operators here. And you can split them in the diagonal contribution, which is when the cubes are the same, and the off-diagonal contribution when the cubes are different to each other. And if the above inequality was correct, it would mean that it's the diagonal terms that are important and the off-diagonal terms are negligible. And this is something that in many occasions happens in harmonic analysis, but here it fails dramatically. So the non-diagonal term could be even r² times bigger than the diagonal term. And there are very easy examples that show this. The inequality here holds, but with an extra massive factor of r² at the front. It's easy to show you cannot do worse than r², because
I mean, the fellows who made the conjecture, what did they prove?
So the first fellow, I think that was Takeuchi, and all of this came from PD, which I don't know anything about, but he claimed it was true, and he used it. And then Mizohata came.
They didn't come up with r².
I don't think so. He just used it as it is without the r². And then Takeuchi came, and Mizohata came and said, wait, this is actually true, and this is how it became a thing. But then later, Stein suggested a conjecture that would connect restriction to Kakea somehow, like a reverse direction. And it's even harder than Mizohata-Takeuchi. So that's one of the reasons to care even this. But yeah, in any case, the r² is easy to show because at every point x, when you calculate the extension operator, we said we look at the cubes passing through that x and counting their contributions. They're at most r² cubes passing through every point x because the cubes have angular separation, so they can't be too many. And so from Cauchy's words, you get immediately this factor, which means that the conjecture holds with the loss r². But if you want to do any better than r², you have to follow some other direction. The coupling estimate won't help. And that's why the r² is non-trivial. One of the reasons it's non-trivial. So I'd just like to explain this bit. This is what we want to show. And for indicator functions, so the weight is an indicator function, there's actually not just the loss we wanted, but the 2/3 exponent in the infinity norm. That is useful later, but anyway. We'll prove a better thing, from which this is a direct corollary. So we want to show that the 2 norm of the operator is controlled by the 2 norm of the initial data with some loss. And this is a loss that we can get. These are cubes. The cubes actually appearing in the wave bucket of the position G. So whatever cubes you have there, those are these cubes. And this is the weight in the cube, the integral of the weight in each cube. Okay? So you look at all those cubes and you look at the one with the maximal weight occupancy, and you calculate the weight there and you raise that to 2/3. That's the loss. Now this has a lot to do with the infinity norm of the X-ray transform, because if you try to calculate the integral of the weight on this cube, it's at most the width, which is r², times the largest number of balls along any one of these lines. So at most an infinity norm. And when you raise this 2/3, the half becomes a third, and that's where the third comes. So this middle estimate is more useful, it's more general. And it follows from a refined restriction inequality. So Stein and Thomas proved some well-known restriction inequality from L2 to L6. And we're going to use a better one that gives what we want. So for now, let's just compare, let's just contrast it with what we would get if we use the actual Stein-Thomas inequality, which says this, that the extension operator is bounded from L2 to L6. We have a 2 norm, so we want to take the left-hand side and use Helder to move towards the 6 norm. So that's what we do here, and we get a loss that has to do with the size of the weight in our ball. And that is a loss that we bring to the front, that will be the loss, and the remaining bit is controlled by the 2 norm of the initial data, that is simply restriction. That's Stein-Thomas. So here is the difference. With classical Stein-Thomas, we get the weight on the whole ball, but with the refined one we'll talk about, we can shrink to just a cube, an r² fat cube, and that's better. And by the way, if you use the whole ball here, the weight on the whole ball is at most the diameter r times the infinity norm of the transform, the X-ray transform. So you get R to the 2/3 rather than R to a third. So this is not even, we know a half, which is trivial. This is much worse than trivial. Okay. The Riffinstein-Thomas inequality is actually structural for the extension operator. So that's why it really helps. And it was proved in the context of the Falconer problem. And it says the following: let's take a function that's a sum of wave buckets, but all of them have roughly the same two norms. Okay, so here are the weights, the tubes in which the extension operator of each wave bucket evolves. Now, Stein-Thomas says this, that we are bounded from L2 to L6. But we want to do better than this. We can't do better in general, but we can in a restricted set on the left-hand side here. So we will be looking at K-rich balls in this picture. So these balls we're looking at have the same width as the cubes, so R², so they cover the cross sections. And we look at, for any K we like, we look at K-rich balls in this picture. So each is intersected by at least K and fewer than 2K cubes. Okay. In this set, UK, the union of these balls, we have an improved estimate. And that features by putting a factor here that's smaller than 1. Okay. So the factor is K, the number of cubes through a single one of these balls, over the number of all cubes in the picture. So this says that the fewer cubes you have through each ball relative to all, the less mass concentration you will have. That is some structural information about how the operator evolves. Okay? These are the waves are evolving in these cubes. So it's all very structural. And yeah, in general, this will be smaller than 1, of course. So we get something better. And we'll do the exact same proof as earlier, the classical Stein-Thomas, but incorporating this improved factor. So here are the tubes and the weight. And we cover the weight by this R², balls according to their level of richness. So you see that this part of the weight is covered by these balls, red balls that are 2 rich. Each has 2 cubes through it. And the rest of it here is covered by 1 rich balls. Okay, each has 1 cube through it. In general, the whole weight will be covered by such balls. Each will have a different level of richness, but some level of richness will be dominant, meaning that it will essentially cover, or it will be responsible for a left-hand side. Our weight will be in those balls mostly. Okay. And the left-hand side will be the same, but only in that nice set in UK. Okay, and then we just do what we did before. We do Helder to go from L2 to L6, and we get this loss here. And then we apply the refined estimate. So there is the 2 norm here, but times the small factor, K over the number of cubes in total. So this is the improvement relative to before. Before we just had this part. And now we want to show that the loss, so this purple part here, the most, that's supreme capital. That is just combinatorial actually. So look at K times the weight in the set. So the weight is just the blue part, okay? We want to look at every red ball in this picture that contains part of the weight and integrate the weight there, but add it up K times. K is the number of cubes through the ball, through every ball. So I'm adding the size of the weight in the ball that many times as the cubes through that ball. And now simply change the order of addition. Instead of looking at every red ball and adding up over the cubes through it, I will take every cube and I will add up over all balls through it. I'll add up the integral of the weight enough. That gives me the weight on the whole cube. And now we just divide through by the denominator, number of cubes. So our quantity was at most the average cube occupancy, which is smaller than the maximal cube occupancy. And that's it. Okay, so this was just combinatorial. I knew the result essentially was a single array for this to work. Right. So this is, I guess, the main result, and gives this nice loss, and the 2/3 power is very useful. So it's very useful because it gives the R to a third, but also it does give us better estimates when our function G is supported on small caps. So I'll just say that for a moment because we're going to use it. A better loss when we have small caps. So when the function G can be defined anywhere, we proved the conjecture with this loss, R to a third. We said earlier, though, that if G is defined on a tiny arc of this length, then the conjecture holds anyway, without a loss at all. So it's natural to wonder what happens in the intermediate situation, where you have a cap of intermediate length. Can we prove the conjecture with a loss in between? And the answer is yes. This is the loss. Doesn't matter exactly what it is. It just is better than R to a third. Okay, and it agrees here with rho equals 1 here, and rho equals R there. Okay. This combines ideas from both directions. So one thing that holds is that because G has a smaller support, its Fourier transform, its extension operator, will be essentially constant in little rectangles, but they're not quite short. They're not as big as in this case, but they're quite short cubes. They still are there. So you can take your weight and cover it up with these areas where everything is essentially constant. So what happens on your weight is only a very tiny proportion relative to what happens in the big picture for the new weight. And that gives you a huge gain. And then eventually, for the new big purple weight, you use the estimate, the loss we talked about all this time, with the refined Stein-Thomas. You get a conjecture for this new weight with such a loss, supremum over all cubes. And if this 2/3 wasn't there, it was 1, it would cancel out your gains from before. But because this 2/3 is there and smaller than 1, it gives you something better. It doesn't matter exactly how, but that is the moral. You combine local constants with the previous estimate, and it works. Okay, so what we remember is that smaller caps give you better estimates than the R to a third. And now I'll just jump to the other direction, the combinatorial part, where we see mainly how we can build weights for which the conjecture holds. It could be a technique to build some weights, and it will give us some intuition about better estimates for some other weights too. So let's say here that here is where G, our function, is defined, close to the north pole of the circle. Okay, simplicity. And we know that the conjecture holds actually for any line when the weight is any line. We can prove that, but let's just pick lines now here that are roughly horizontal. Okay, just like the ones we were talking about earlier. We said Planck-Sorel holds for every one of these lines, and mainly I'm looking at lines whose direction is separated from the normals to my cap. Okay. Now this is Planck-Sorel, yes, but it can be interpreted as the conjecture holding for this line or for the one neighborhood of the line. Because if you take any other line in this picture and see how it hits your weight, it hits it at width only 1. And that 1 is the constant at the front. That is the infinity norm of the X-ray transform here. So Planck-Sorel in this case is simply Mizohata-Takeuchi for this line. So because of the conjecture holds for all such lines, there is a way to upgrade it to holding for long line segments, or for slabs, in other words, as long as the slabs, we'll see, are long enough to cover the cross sections of our tubes. So they should have to be R2½ long. And similarly, by the way, we can prove that Mizohata-Takeuchi holds for any curve with controlled slopes using not Planck-Sorel, but some induction scales. And then you can upgrade then the conjecture from this picture to unions of curved slabs of length R². So this is how you would get these nice weights. And let's just see why this makes any sense, this upgrade, just for the straight slabs, okay, not curved slabs. So here they are. The weight is a sum of these indicator functions of these slabs that are r½ long, and importantly, their directions are controlled. So their slopes are, give or take, 45 degrees from the horizontal direction. Okay. We look at every slab S and want to understand the operator squared on that slab. Remember, all that matters is the tubes that pass through S. Those are the only ones that will determine the operator at S. No other tubes will matter. So I'm just gonna do the same integral, but only for that part of the function, the sum of the wave packets through S. That's a new function, part of the original wave packet decomposition. And I'm integrating on a horizontal thing, nearly horizontal thing. So by Plancherel, I get at most the integral of the initial data. Now this initial data is part of the original wave packet decomposition, and the wave packets are orthogonal to each other. So I have that the Pythagorean theorem holds for this new function. And actually, it's really a quality algorithm. Okay, this step here was just Mizohata-Takeuchi for this line. That is all. Okay, and then I just add up over the slabs in the picture. Okay, to get my left-hand side. For every single slab, the integral is this thing. So I just write that out. So for every single slab, I'm looking at all the tubes through the slab, and I'm counting the I'm adding the contribution of each one. Again, like before, we change the order of addition. Instead of doing this, we can, for every single tube, look at all the slabs through the tube and add the contribution of the tube that many times. Okay. So I'm adding for every tube that integral, but this many times. Okay. And now that's where it was important that the slabs are long. They go from one side of the tube to the other. So if you take any line in the tube, it will hit all of them. Okay. And that's why this number here is at most the infinity norm of the Essay transfer. Okay, and the conjecture holds because of this. So just by Plancherel or Mizohata-Takeuchi for any single of the lines, you turn it into a combinatorial problem. Okay, but what would you do if the slabs were short? Like this final thing wouldn't work anymore. Okay? A line wouldn't have to hit all of them. And what would you do if the slabs had the, I don't know, higher slopes? Then you'd get losses here, actually. So it would be more complicated. And that's the last thing I want to talk about. So really what's going on here, is that at every slab, you have orthogonality of the wave packets through the slab. Roughly speaking, this is what happens. This is a very special case where the previous stuff we said about that mass decoupling estimate being wrong, it all holds here. That is extremely special. So we'd like to see if we shorten the slabs or change their directions, do we have some level of orthogonality between different wave packets, which could help us with. So just to sum up so far, I'm going to focus on slabs. We know the conjecture holds for these merely horizontal long slabs. We proved it with an R2/3 loss in the general case, and the general case are slabs of width 1, so they're not long at all, they're just little balls. And we'd like to see if in the intermediate case, where the slabs are not that long, or they're not that short, if we get something better than the worst thing possible. And also how is this nearly horizontal situation helping? Do we need it? Can we say anything without this assumption? Right, and it's all about orthogonality here. And so here we are, we have a general weight and the function on the left. We could cut up our function in smaller patches, in smaller parts. So in caps tau, we don't know what length these have. They could be quite long, but we want to cut up in caps tau so that different caps are orthogonal essentially on our weight. This is something we would like to do. And the question is, what are the smallest, for a given weight, what are the smallest caps you can split in here, so that you have the total contribution can be decoupled in the contributions of the individual caps. Okay. Such an inequality would mean that the G tau are different, are orthogonal essentially for the different caps tau, roughly speaking. And remember, for every small cap, we had improved Mizohata-Takeuchi estimates. So if you prove such a decoupling inequality, you inherit that better loss from the small caps for your bigger one. So it would be good. Okay. And we can say something about this question when the weight is a union of slabs, like before. But there is a difference between the case where the slabs are merely horizontal, or in the case where they are allowed to have any possible direction. Mainly the length of these caps is that we can ensure decoupling is smaller in the horizontal case, that's good, than in the general case. But we still get something in both cases. So split in rho to -½ caps and get decoupling in the horizontal case, nearly horizontal case, meaning that the caps are quite short. They are have the reciprocal length of slabs. And in the general, so that would give us the conjecture for these weights with whatever loss we proved earlier for these caps. So we inherit that loss. And that's better than R2/3. In the general case, we cannot do decoupling in such small caps, but we can use slightly larger caps at the square root of the previous length. And that gives automatically Mizohata-Takeuchi with a better loss again than a third. And just for a reality check, what would happen if the slabs were long, just like in the combinatorial argument we saw earlier? In the horizontal case, we proved that there is no loss whatsoever. Right? The conjecture holds for those slabs. And indeed, that's the case where rho equals R here, and you get no loss, even from this perspective. And in the other case, where you allow the R½ slabs to point anywhere, by replacing rho equals R here, you get R2/6 loss, which is better than R2/3. So these are cases where you do better than the R2/3 loss. Okay. I guess I will stop here, proving such estimates here, like orthogonality between the different G tau is really just geometric. There is no harmonic analysis. And there you just make a picture when can they, how can they interact with this lab, and it works. So I'll stop here. Thank you.
Questions from Marina?
Yes, I can ask a question. Nobody's asking.
Oh, it's okay. You don't have this.
No, it's with friendly questions. The 1/3, is it useful for anything? In other words, you mentioned PDE, where these people made a.
It's not, as far as I know.
What did they need? So it turned out that what the guy claimed he could prove was wrong.
Yeah, yeah.
And, is some power enough for that application?
I don't understand that, but so I know someone who does PD and told me after he heard this that he had made up the conjecture himself, and he just was trying to show it for something about wave scattering, but I cannot understand what it is. So and the R2/3, I talked to him about it, and it's not useful.
This conjecture is believed?
Some people are wildly against it,
Yeah,
because it seems very wrong somehow, but yeah, we'll see. But then if this was wrong, then Stein's conjecture would be wrong, and Stein tended to be correct.
What was his conjecture?
His conjecture was that if you have your G here, and the weight and the integral of this would be at most the integral.
I see. So with that 6.
Yeah. Times so here you would get for every omega, you'd get the supremum of the integral of the weight on every line parallel to the normal domain. So it is even finer.
What's the exponent there? For any.
So squared.
Okay.
And 2, yeah. So if this was wrong, his conjecture would also be wrong. Also, if you prove this conjecture, the Mizohata-Takeuchi one, you can prove multilinear restriction at the endpoint, which is something harmonic analysts care about. So there are applications in harmonic analysis too.
Really, at the endpoint, even though you're losing epsilon there all the time?
I mean, okay, I guess I mean the exponent point.
Not the choice.
Yeah. So that would be a combination of this weighted estimate on the operator with what Larry Guth was doing for multilinear Kakeya. So if you combine that argument with this, like the start of the argument, you would get a restriction. Oh, wait, sorry, you would, okay, so the conjecture itself doesn't have losses.
Yeah.
They have losses.
Yeah, you always have with the empathy.
But the conjecture doesn't have losses, so it would be actually endpoint.
I got it, yeah. Yeah. But these decoupling always gives.
It gives losses, yeah.
So Marina, can you say something better if you assume that your functions is a product of one-dimensional functions?
Here it's just a one-dimensional function and we cannot do any better.
So you don't consider the multidimensional?
We do. So in higher dimensions, the losses are to the n minus 1 over n plus 1.
Okay. Yeah, I'm asking about this because the last year Camille Muscalo showed that the restriction conjecture holds for functions which are product of one-dimensional functions, as well as Kakeya with his student.
Interesting. Okay, I'll
So that's the first
case
where you have the support that the restriction conjecture may be true in higher dimensions.
I'll think about that. Yeah. What I can say about higher dimensions, though, is that if you prove the conjecture in any dimension, it automatically holds for all lower, which is not true necessarily for restriction.
Any more questions? Okay, if not, let's thank Marina again.